This video is on immunodiagnosis and immunotherapy. We're going to talk about the structure and function and revise the different antibodies our body produces, and then talk about monoclonal antibodies and their role in diagnosis and therapy. Okay, so I hope that this will mostly come as revision for you guys, but this is an antibody. Um, there are two parts to an antibody, the FAB and the FC segments. FAB is where the antigen binding site is. It's made up of a variable light and heavy chains, and this region where the antigen binds is unique for each antigen. So the principle is that our body produces an innumerable number of B cells, which produces every permutation of antigens. So our body can technically respond to everything. So yeah, this makes us respond to any antigen possible. The FC region is made up of heavy chains. It's the constant region, and it determines the type of immunoglobulin you're going to make. So it also determines the function of the antibody because this region here will bind to an immune cell down here. It can bind to complement, etc. While this binds to the antigen, can bind to other aspects of the immune um, system to guide the response to this antigen. Okay, so there are five different isotypes or types of antibodies with IgG, IgD, E, M, and A. The reason why they're different is not only because they form different structures like this, but the main key difference is that they have different FC with different heavy chains. Like I said here, the thing that determines the type of immunoglobulin is the heavy chain here. B cells, essentially, when there's an infection of sorts, when there's a response to an antigen, we start with an IgM response, and then we can produce IgG later, and we can essentially produce a vast different variety of isotypes um, for the same infection as what is necessary. So we're just going to go through the characteristics of these different ones. Uh, okay. Um, IgM is going to be a pentamer or hexamer, while IgD is a monomer. IgD's role is actually unclear, and it is believed to be a receptor of just naive B cells that is not secreted. So it's just found on the surface of B cells. So we can more or less just ignore that. IgM activates complement. Uh, so it has a lot of these different antigen binding sites. That means that it has high avidity in total. So there's a difference between affinity and avidity. Affinity refers to the binding strength of each antigen presenting site. Avidity refers to the total sum of the binding strength of the whole isotope. Since there's a lot of different binding sites, it has a high avidity but low affinity. So it compensates for the low affinity. Uh, yep. IgG is a monomer um, over here. It's going to be the second one that's produced in response to an infection, and it has a much greater affinity than IgM, and it basically does everything that we want an antibody to do. So it can neutralize the antigen by itself, it can use complement, it can, and it's also transmitted such that it provides neonatal immunity. IgA is a little bit special. There are two different types of IgA. There's serum IgA and mucosal IgA. In this picture here, we see a dimer, which is going to be the um, mucosal IgA. In reality, you have a serum IgA, which is a monomer, which is found in the blood serum. This mainly just activates the innate immune system uh, and has an inflammatory effect. Mucosal IgA does not, so it's not inflammatory because it's found in the respiratory and gastrointestinal tracts. Uh, so we don't really want to have like a super big inflammatory response in that area. It doesn't activate complement, uh, and it's also found in breast milk and colostrum, meaning it also provides neonatal immunity. It also has high affinity as well. So IgE is the final monomer in response to helminths and different antigens, which leads to an allergic reaction. It's found on the surface of granulocytes, so that this includes basophils, eosinophils, and neutrophils. For example, and mast cells as well, which is why it's so linked to allergies because the release of histamine from these basophils and mast cells regulates a lot of what we see in an IgE response. It doesn't neutralize, uh, and it doesn't have a complement effect, but rather it just sits on the surface of these granulocytes such that when the antigen binds to IgE, it just releases the granules, or it basically causes the function of the granulocytes to start. So it activates these granulocytes. Okay, moving on. Monoclonal antibodies. Firstly, what is a monoclonal antibody? There are two different types. We can say that there are polyclonal and monoclonal antibodies. In a normal response to an antigen, our body creates many different B cells are activated. So this is a concept that I think is a little bit tricky to understand because we often think of just one B cell that's for one antigen, but in reality, the an antigen can be anything that our body's responding to. An antigen has different epitopes, which are different parts of the antigen that we can respond to. So for the same antigen, we can have multiple B cells that are activated, which produces antibodies to different epitopes or different parts of the same antigen. Therefore, if you just have a normal antigen response, our body can actually create a lot of different B cells, which gives us a lot of different antibodies, but they target the same antigen, and this is a polyclonal response because there are different uh, different antibodies being produced. A monoclonal response is for the same antigen for the same epitope, it's only by the one singular B cell. We can create monoclonal antibodies through isolating. Essentially, we introduce the antigen into some organism. We get an antibody forming cell, like a B cell, and then we fuse it with a tumor cell to form a hybridoma. And then this hybridoma can allows us the replicative capacity of a tumor cell, so we can just spam it and just make as many monoclonal antibodies as we want. Okay. Um, this is going into the diagnostic capability of a monoclonal antibody. So when we see antibodies in the blood, for example, we can measure antibodies in the blood through three different ways. Measuring antibodies isn't the best title here, but I hope it makes sense as we go forth. So, in precipitation-based analysis, we can get a soluble antigen. If you get a soluble antigen and a soluble antibody, it forms an insoluble precipitate. So we can measure the amount of soluble antigen in a sample by combining it with the necessary amount of soluble antibody. Um, and we can measure the if we measure the precipitate, that gives us an idea of how much of the antigen was there. So this is where monoclonal antibodies come in because then we can just produce these soluble antibodies, right? Like it allows us to measure stuff. It's just the principle of why we're learning this. There are two different ways to measure stuff when it's in a fluid like this. One is called turbidimetry. Turbid means it refers to the cloudiness or the turbidness of the sample. Nephelometry is another one. The only difference is just that in this turbidimetry, you have a detector on the other side, and we read how cloudy it is. But in nephelometry, we read the scattered light from the formation of the precipitate. So it's just two methods to measure how much precipitate forms, which tells us how much antigen is there. Okay, another one is through immunodiffusion. So if we're going to use something like a gel instead of a solution like that, um, the idea is basically that you have, so I have a agar plate or a gel plate with antibodies throughout, and now I am adding an antigen into the middle of that plate. As the antigen sort of spreads out, the concentration of the antigen decreases to such a point where uh, the concentration of the antigen will be the same as the concentration of the antibody. So essentially, if you have some antigen like antigen solution that is very concentrated, then it can reach out much further until it forms the precipitation ring. But if it's much lesser, the concentration is much lesser, then it can only reach out so much until it forms the precipitation ring. That's just the principle of immunodiffusion, like behind immunodiffusion. The second one we're going to talk about is agglutination-based measurement. Um, this is actually important to know what the Coombs test is. So the difference between agglutination and precipitation was in agglutination, we have the antigen that is on the surface of an insoluble particle and an antibody, which eventually forms these lattices, which changes which like causes agglutination basically. Okay, so there is, and there's something called a direct Coombs test and an indirect Coombs test. In a direct Coombs test, often used for something like hemolytic anemia, where there's like antibodies reacting with red blood cells. Okay, so the key thing that this serves to do is to measure the antibodies on the surface of the red blood cell. Okay. Um, this gets a bit confusing because we use the word antigen on the insoluble particle, but in this case, what is happening is we have a blood sample with red blood cells. This blood sample with red blood cells has an immunoglobulins or an anti-red blood cell antibodies on its surface. Once we get it, we add this antibody. So we have a monoclonal antibody which binds to the anti-RBC antibody, which then causes this agglutination process. So the antibody on the surface of the red blood cell, the anti-RBC antibody, is kind of like the antigen of this reaction. In the indirect Coombs test, we're measuring the plasma instead. So we instead of washing the red blood cells, we're removing the red blood cells, and we've just got uh, we're basically adding the red blood cells and the antibodies. So yep, that's that. The last one is labeled. The idea behind labeled is there is some substrate that's being added, which changes some color, which is useful in some diagnosis. The most common one is enzyme-linked immunosorbent assay, or ELISA. In this one, we have an antigen, and then we add the patient's serum. Now we don't. What we're trying to find out is if the patient serum has antibodies. So we don't actually know if it has antibodies. So we once we add the serum, then we add an enzyme-labeled antibody, which binds to the serum's antibody. So similar to the previous one, it's an anti-antibody antibody. If the serum had antibodies, then it would bind to it, and then once you add the substrate, it would react with the enzyme-linked antibody, which causes a change in color. And we can titrate down to the lowest amount of color to figure out the concentration of the serum. And then there's a couple of different types in this category, such as immunohistochemistry, immunofluorescence, and flow cytometry, which I think aren't as important, but if you know the name and maybe what roughly it is, that's good enough. Oops, okay. All right, so the final category is therapy. All right, so we can use monoclonal antibodies in therapy. There are different types of monoclonal antibodies. Uh, the process by which we talked about earlier with mice hybridomas and generating antibodies that way, that's going to be like that's from a foreign source, right? So you can expect an immune reaction to that from our body. We want to use stuff that's as fully human as possible to prevent that. Yeah, okay. We have a couple of examples, rheumatoid, chronic lymphocytic leukemia, and cancer as the three examples that we want to know. Okay, in CLL, this is a leukemia of lymphocytes, so we have a lot of B lymphocytes. All right. These B lymphocytes, they express a protein on the surface called CD20. Now we can target that. That means that we can now target these B cells by having a monoclonal antibody against CD20, which is rituximab. And it's one of the three therapy regimes, which is FCR, which are these three drugs. The, there are two ways by which it works. It works through antibody-dependent cellular cytotoxicity, which is a fancy way of saying this rituximab will bind to something like an NK cell classically. It can be other things like neutrophils or macrophages, anything that will kill uh, the cell. So it forms the FC segment will bind to the NK cell and then trigger it to kill the B cell. It also works through complement activation, which does the membrane attack complex of I think it's 5 C5b, oh sorry, C3b in this picture, which then kills the cell. So yeah, rheumatoid arthritis. All right, so I think we want to broadly understand that in this case we have interaction with the immune system to kill what we want to kill. In rheumatoid, it's a little bit different. Instead of promoting immune function, we actually inhibit immune function because rheumatoid is an autoimmune reaction. What happens is there's a type 4 hypersensitivity, meaning there's a T cell response that is mediated by a bunch of cytokines, notably interferon gamma and tumor necrosis factor alpha. TNF alpha is what we want to inhibit. By inhibiting it through infliximab, we stop the disease progression, we stop the formation of matrix metalloproteases, the MMPs, which prevent joint destruction, and we stop production of rank ligands, which cause the bone destruction. We also stop activation and basically bringing in of other immune cells as well. Okay, so this one was to promote immune function. This is to inhibit immune function. In cancer, we want to promote immune function again because if we do that, that allows us to kill tumor cells. Uh, Basically, the idea here is that we're inhibiting the T cell deactivation. To understand this, let's start with T cell activation. So T cells are activated when an antigen presenting cell shows it an antigen, it reads it using the TCR or the T cell receptor, and at the same time, you have a co-stimulatory signal with CD28 on this T cell and CD80 or 86, which is also the same as B7.1 or B7.2. But you have CD20, CD80, and 86, which forms sort of like the confirmatory signal that this T cell is now going to be activated for function. Now, T cells need to be deactivated after a while because if we have chronic activation, it causes autoimmune conditions. Uh, we have two mechanisms by which we deactivate T cells. The first one is CTLA4. CTLA4 is found on the surface of the T cell. It mimics CD28 and it binds to CD80 and 86 with greater affinity than CD28. So basically, once it becomes activated, the T cell is in a constant, like the balance is shifted now that it's activated. Now it wants to stop itself. So after it works for a while, eventually this interaction works where CTLA4 binds to CD80 and 86, and then you get a stop signal which stops its function and deactivates it. We can stop this by having an anti-CTLA4 monoclonal antibody, which basically stops the stop function here. And the drug is called ipilimumab. Yeah, so the second way by which we can deactivate T cells is through PD1 and PDL1 or PD ligand 1 and ligand 2. So PD1, much like CD20, is going to be found on the surface of activated T cells. PDL1 and L2 are going to be found on other cells. PDL1 is broadly expressed by a lot of different cells. PDL2 is again only expressed by APCs, much like so it basically mimics the CD80 and 86 function. And the binding of those two will stop its function. It's a stop signal, and we can counter the stop signal by having an anti-PD1 monoclonal antibody. And that is basically this idea here. And when we use these two together, we get a good response, which is, I think, being trialed still. But yeah, that is the end of this video.